Hey there, STEM Chemistry. This is Miss Ruark, and this is the very first podcast of our excellent, most wonderful, awesome year together. All right, so how does this work? Well, I gave you a fill-in-the-blank notes at school. You come home and watch the video. Sometimes I'm doing writing on it, sometimes I'm not. Unfortunately, I'm not going to do a lot of writing on this one because I left my tablet with my nice little pen at school. But you still get to hear my lovely voice and spend a little bit less than 15 minutes with me every time you watch one. You're happy. All right, while you're watching this, if it goes too fast, pause it, rewind it, watch it again if you need to. These will be posted all year long, so you can watch them again before you do your test, before you take any exams, etc. All right. So let's just get started. Okay, on this one we're going to talk about isotopes, but to get to isotopes we have to cover some ground information first. There's my pen. All right, so let's talk about atomic structure. We know that the atom contains two regions in it. One region is the nucleus. That's the inside of the atom. It's the one that contains the mass of the atom. Okay, so the mass of the atom is there in the nucleus. Why? Because the protons and the neutrons are so heavy. All right, in there we have protons. And protons, the symbol for proton is a P with a plus sign, like a superscript. Okay, P plus. And you'll see me write that all the time because I'm too lazy to write out proton. It's the truth. Okay, and the proton has a charge of positive charge. Its actual mass, if you look at this is an extremely small number. How do we know? Because it has a negative 27 there. I did a horrible job of circling that, so let's take that off. All right, it has a negative 27 there, which means that that number is going to be extremely small. Why? Because that decimal is going to go 27 times that way. So we're going to have a lot of zeros in front of it. So it's an extremely small mass, but if you think about it, the mass in terms of subatomic particles is pretty heavy. But we can't think of it that way because we're so big compared to it. So we have to give it a relative mass that we can use to compare, and we give it a relative mass of 1. And that makes it easy when we're counting how many protons are inside the nucleus. We can say the number of protons is equal to the mass of the protons. Oh, that's awesome. All right, the other particle that we have in there is called a neutron. The symbol for a neutron is a lowercase n with a funky little circle like a degree sign almost. Okay, this would be the neutron. Neutrons are neutral in charge, so they have no charge. The mass of a neutron, look at it, it's very similar to the mass of a proton. And so we say, well, if they're so close, they're pretty much the same. Well, if the relative mass of a proton is 1, then the relative mass of a neutron has to be 1 as well. And so that way we can count up how many protons and neutrons we have inside the nucleus, and that'll tell us the mass, and I'm putting up quotations, little air quotations, you can't see them, but it gives us the mass of the nucleus in relative terms so we can think about it and compare about it and put our hands on it, our fingers on it, our minds on it. Okay, here we have the outside of the nucleus, or the outside of the nucleus is what we would refer to as the electron cloud, and that would be where the volume of the atom is at, the volume. And the reason for the volume is because there's a lot of little electrons floating around in a huge amount of space. All right, so to give you perspective on this, if we were down on the 50-yard line of the football field and we took one of those little green peas, you know, the LaSure or whatever they call them, the really sweet little green peas, they taste really good, come in the silver can. I can't think what they're called. But if we take one of those and we put it on the 50-yard line in the very center of the 50-yard line, okay, and we look all around us in the stadium, that little P would be the nucleus containing the protons and the neutrons, and all around us in the stadium, up into the concession areas, that would be the electron cloud. So the nucleus is extremely small but extremely dense, and the electron cloud is extremely big but extremely light. Okay, the electrons that are floating around in there have a symbol that's E with a negative. Why? Because the charge of those are negative. And if you look at the mass, you're like, wow, that's a big number. It's actually not, because it's a negative 31, which means it's even smaller than the mass of a proton and a neutron. And so the mass of an electron is so much smaller than a proton and a neutron, we say the relative mass is equal to 0. Okay, so here's another picture for you. If you go to the doctor and you get your mass or your weight taken. You jump on the scale, and then you jump off and you lose an eyelash. You go, wait, doctor, you got to take my weight again because I think I just lost some weight. He'd probably look at you like you're crazy. And the reason for that is because that eyelash, it's not heavy. Okay, this is the same thing as the electron. The weight is so small that we say it's negligible, which means it doesn't matter. All right, so looking at your periodic table, you've probably seen this before. Oh, yes, and we can spell anything. Well, almost anything with our periodic table. But anyways, looking at this, you've probably seen it, so I'm going to go through this quick. Here you have the atomic number, which is the number of protons. That's the identity of the element. It tells you exactly what element it is because it's specific for each individual element. So barium is the only one with 56 protons, and nitrogen is the only one with 7 protons. And remember, if we change the number of protons, you're going to change the identity of that element. All right, then you have the element name. Now, the element name is not always on the periodic table. It just depends on who made that table. But the atomic number is. All right, then we also have our element symbols. Now, the symbols and the names don't always match up, and that's because the symbols are from the old names, which are usually Latin-based or Greek-based, and some of them, I believe, are German, but I'm not positive. All right, then you have your element symbols. It's 1 or 2 letters, no more than that, except for the funny little uns at the bottom, but I think most of them have a name by now, and that's only because they never really named them. All right, and it's the Latin number for 100 and whatever. Anyway, so 1 or 2 letters, first letter is always going to be uppercase, and then if there is a second letter, it's always going to be lowercase. Pretty easy. All right, and then you have your average atomic mass. That should always be on your periodic table as well, and that is based on the percent abundance of the naturally occurring isotopes. Percent abundance. That's going to be something we need to remember, so don't forget that. All right. I said if you change the number of protons, you get a new element. And we talked in class that if you change the number of electrons, you get an ion with a charge. So what happens if we change the number of neutrons? That would be pretty cool, right? Well, you get an isotope. Okay, so what's an isotope? An isotope is an atom with the same number of protons, but a different number of neutrons. And remember, the neutrons are pretty heavy, so if you change the number of neutrons, you're going to change the mass, so it has a different mass. All right, so here are 3 isotopes of hydrogen. You have hydrogen 1, here, and it is protium. Hydrogen 2 is deuterium, and hydrogen 3 is tritium. Okay, here with hydrogen 1, it has 1 proton, it has no neutrons, and it has 1 electron. It is the only element on the periodic table that has 0 neutrons. It's pretty special. All right, and it is 99.985% abundant. So it is the most abundant form of hydrogen that you would come across naturally out in public. Well, you wouldn't find it in public, but out in nature, I guess is what I'm trying to say. But I said naturally, and it didn't work right. Okay. Anyways, hydrogen 2, or H2, deuterium, is 0.015% abundant, and it has 1 proton and 1 neutron. And then hydrogen 3, tritium, is very, very rare. It's radioactive, which means it spontaneously breaks down, and it has 1 proton and 2 neutrons, and then the 1 electron floating around. All right, so if you've noticed, there's a trend here. The number here, the number that we call it, hydrogen 1, hydrogen 2, hydrogen 3, goes along with the number of subatomic particles in the nucleus. So how many protons and neutrons? All right, so this is one way, this right here is one way that we can represent an isotope. We call that isotope notation. And it's got the hydrogen, the symbol for the hydrogen, and then it has a proton number down here, or atomic number. And then the top number is what we would call the mass number. And the mass number tells us how many protons and neutrons are inside of the nucleus. Okay, all right. Then you can also represent it by doing hyphen notation, which would be H-3 or H-3 to represent tritium. If it was deuterium, we would do H-2. And if it was protium, we would do H-1. And when you're talking about isotopes, you do have to show the mass number, because the mass number determines which isotope you have, and they're all just slightly different. So you do have to actually show, when we're asking for isotopes, what your mass number is. All right, well, Here's the question. Oh, I did it too quick. Darn. All right. So here's my question for you. If hydrogen 1 has a mass of 1, and hydrogen 2 has a mass of 2, and hydrogen 3 has a mass of 3, and the average atomic mass on the periodic table should be 2, but it's not. It's 1.008. Why? Why? All right, well, the reason for that is because it's based on percent abundance. So think about your grades. Your grades are based on percent weights, right? Your tests are 50%, your quizzes and your labs are 40, and then your daily work is 10. So each one of your assignments has a different weight. Well, the same thing is true here. It's just based on how abundant they are. So here's a problem for you to try. And we're going to do some more of these in class. So here we have rubidium. Rubidium is a picture of it right here. It's pretty. It's a soft silvery white metal that has two common isotopes, rubidium 85 and rubidium 87. If the abundance of rubidium 85 is 72.2% and the abundance of rubidium 87 is 27.8%, well then what would be the average atomic mass of rubidium? All right, so to figure this out, we're going to take our percent abundance here and our percent abundance here, and we're going to multiply them by the mass of each element. Okay, so if rubidium 85 is 72.2% abundant, we're going to multiply that by the mass of rubidium 85. Now, sometimes they give you an actual atomic mass and it'll say a number AMU. If it doesn't, then you're going to use this mass number right here. Okay, and we don't like to use percents because they're kind of screwy. So instead of doing that, we're going to change that into decimal form, which would be the relative abundance. So when we change that, to do the first one, we would do 72.2 changes into 0.722, and we multiply that by 85, which is the mass, and we get 61.37. Well, we got to do the same thing for rubidium 87. So here you go. All right, now, that's not the whole story, though. They need to know the average atomic mass of rubidium, which is all of the isotopes together. So in order to figure that out, we're going to add those two numbers together. And you get 85.556 AMU. Do you want to check your work? Sure you do. We're all smart. We don't want any issues here. We don't want any errors, so let's check our work. And if we look at the periodic table, we can see that rubidium has an average atomic mass of 85.447. And guess what? We used mass numbers instead of actual masses, so it works. Okay, it's close enough. All right, so this just kind of gives you an idea as to what we're going to be doing when you come to class next class. We're going to be doing an activity where you're classifying a made-up element based on its average atomic mass. All right, and I always like to leave my students with a little something to say thanks for listening, and it's usually something silly like this. All right, and I'll see you in class.